now.
Hey, hello and welcome to our design, installation and commissioning of STEAM live event. So today we'll be looking at understanding the current practices in STEAM and condensate systems and the factors to be considered in their design. Yeah. So I first want to thank you very much for signing up for today's topic, and we are overwhelmed by the positive response. So thank you for your engagement. All right. So I'd like to open this session by introducing your presenter, who will be Nick Wisby. And Nick is a dedicated and results-oriented technical sales support engineer with a rich background in engineering industries with over 2 decades of experience in technical applications, electrical engineering, control and instrumentation, and STEAM. So he's been part of Spirax-Sarco for over 7 years now, and is currently based in our Spirax-Sarco East Africa office. Yeah, he based in Kenya. Myself, Anthony Macharia, I am the sales manager for Spirax-Sarco East Africa, and I'll be facilitating this live event and pick up any questions that you may have. Yeah. Also, we do have Cornelia Schenk as one of our producers. He's a current national sales manager for Spirax-Sarco South Africa, and we welcome you. So we can go next, maybe. So the housekeeping. So basically, we just would like to give you a few housekeeping rules as usual. So this session will be approximately 1.5 hours. And it will have maybe like a 60-minute presentation with a 15 minutes Q&A at the end. And we will mute all of your microphones throughout the session. And when you want to do or submit a question, you will do it on the Q&A pane, which will be on your dashboard. Yeah. Yes, so we can go next. So the questions will only be seen by the hosts. Yeah, and if it's be possible, we may not be possible to answer all the questions during the Q&A session. We will reach out to you to ensure that all of your questions are answered at a later stage. And so with that, I would advise you to please complete the feedback form after the webinar. We'll really appreciate that. And the housekeeping, in terms of questions, you will see this live event Q&A panel. Yeah. So just type in your question at the compose box and then click select send. So just select send and it will come to us. If you want to post it anonymously, just select anonymous before you click send. Yeah. So we will see it and we will publish your question and it will appear on everyone's featured tab along with the answer. Yeah. So I believe I'll hand over to Nick, who's going to be our presenter, to proceed on for the rest of the live event.
Thank you very much. So good morning, everyone, and thank you very much for joining us. It's a pleasure to have you. So first we'll cover the agenda. So in this course, we're going to sort of try and cover as it said, the design, installation and commissioning. So it gives you a basic knowledge on those fields, and we try to break it down. So first we'll cover the properties of steam. Sorry, the order's a bit wrong. Sorry, first we will cover who are Spirax. We did this the last time. It's just so that you guys know where your nearest agent is available and any contact details you require. We'll cover the properties of steam, followed by pipe sizing. Strainers will be next, line gradient, steam trapping, separators, air vents, minimizing water hammer, safe isolation, warming up of a cold system, expansion and support, and then finally safety. So who are we? So those of you that joined the last one, you'll be aware. So we were first started in 1888 in the UK by two gentlemen, one called Sanders and one called Raiders. So that formed the Sarco, the Sarco of our name. So effectively it's the breakup of the initials there. In 1932, we brought out a product range that we marketed under the Spirax logo. So therefore, we formed them together and made the Spirax-Sarco. We have 145 operating companies worldwide. So that's with 180 plus local sales offices in 55 countries. The figures on here are a little low. We're over 10,000 now with employees and over 2,000 service engineers. So the idea is you always have somebody local. We have 29 manufacturing sites on 4 continents. And our global HQ, as I mentioned, is in Cheltenham, which is in the UK. We also have 59 customer training centres, so centres that are specifically designed for customers to come in, do a course with us, receive a qualification. So under the Spirax structure, we've just recently gone for a name change, so I will update this next time. So we are now Spirax-Sarco Group, under which we have various different companies. Spirax-Sarco, as you already know because you're here. Gestra is a very similar company, which I imagine many of you would have seen on site too. Cotopaxi, which deals with the I think it's electrical tracing, things like that. Chromolux, which is an American firm that deals with our heating elements. Thermolux, Thermocokes, which is very similar to Cotopaxi, I think, and Watson Marlow. Our main product areas are, as you can see, so we cover everything from boiler controls, clean steam, humidification, compressed air, steam traps, pipeline auxiliaries, isolation valves, many more as well. So although we are steam, we are pretty much everything to do with your manufacturing. Servicing, we can offer sort of 24-hour priority response in many areas. Health and safety compliance with local legislation. Steam audits, so steam system audits, we can take a look at your system and tell you if there's any improvements you can make or if there's anywhere that is running less efficient. And valve reconditioning, so we can repair. I always show this slide because why we are experts is because we actually use boilers. This is sat in our training centre in the UK. It's nice and shiny because we have customers that walk around it. But yeah, we take this apart, we service it, we run it, we do all the things that you would do on site. So we have practical knowledge. It's not just theory. So we will cover properties of steam now. So the advantage of steam is the temperature is uniform in comparison to, say, oil and water. So as it says there, high heat content, 5 or 6 times higher than hot water. Steam lines are relatively lightweight because of you can pressurize them, you can reduce the size, so therefore you reduce the weight of the pipe. Steam flows with pressure drops, so there's no need for circulating pumps. Effectively, this is what we call a pool system. So by the collapsing of steam in your process, that then pulls a vacuum, which then pulls fresh steam back through. Loads can be changed at will, no need to balance the system. So effectively, yeah, if you want 500 kilograms 1 hour, but then you want 1,000 the next, you don't need to resize pipes, you don't need to rebalance the system. There's no electrical load to try and even out across your banks. And there's no need for drain down for line maintenance. So most of this can be isolated. You can take various different points, strip them down, fix them, so you can still stay up and running. We're a pressurized system for water, for instance. It's although you could argue you still have the same isolation, it's a little bit more difficult because of pumps. And again, as we said, uniform temperature gradient. So there is a relationship between pressure and temperature. The higher the pressure, the higher the temperature. We're only close in wet saturated steam now. Superheated is a different beast. So heat transfer coefficients of steam are often 2 times the water. So that's just saying the amount of heat it will give up when it touches a surface or a process compared to hot water, or I think it's slightly lower than that for hot oil, for thermal oil, but not by much. So distribution under pressure. So high pressure, lower meters cubed an hour, a kilogram even, so smaller pipework. So effectively what we're saying is the more pressure you put in this, the square area changes of the steam, so you make it more dense. Therefore, you can reduce the pipe size, which makes it cheaper for runs. But we all know from our own boilers are expensive to run. There's no getting away from that, whether you're using biomass or HF4 or gas or many others. The process itself is cheaper because the equipment can be smaller. So if you take, say, a water system, for instance, the pipe works would be bigger, which means that you're reducing valves, your process equipment would have to be larger to take that load. You've got the extra weight of the pipes, so they tend to have to be better supported, thicker materials, and the HF, so the energy it actually gives up is much less. So lower capital cost, again, this refers to the cost of pipes. So if you can make a smaller pipe, there is going to be a smaller cost. So the difference between a DN50 and a DN80 pipe, I think this is based on Schedule 40 carbon steel, is 40% of the cost. Dry steam at point of usage. So yeah, if you speed this up, if you compress it more, you make it hotter, it's going to be drier when you're using it. Less inefficiency, heat loss. So as you reduce this, and again, you speed up the load, you reduce the heat loss because it's not in that pipe for as long. So you can see up to 20% less heat loss. And the boiler operates at optimum conditions. So this is all based on your boiler running on the plate values that you have on your boiler. If you have a 10 bar boiler and you run it at 7 bar, you're not running that boiler as efficient as it was designed to. So we need to, as users of steam, we need to make sure our boilers are running at the point where they're meant to. It is tempting to turn them down, to lower the pressure, to make them cheaper. But when you start including the inefficiencies you've then brought into the steam system, it's not as energy saving as you would believe. Thermal storage capacity of a boiler is increased. Yeah, so again, this is talking about using the plate values. So if you're pressurizing water at 10 bar, it's got more heat, more steam capacity than if it's at 7 bar. It's as simple as that. And more efficient under fluctuating loads. So if you have a higher pressure, higher volume, if you suddenly draw down quite a bit of steam, it's less likely to starve your process because your boiler is sized correctly and it's being used correctly. And reduce risk of priming and carryover. So the higher the pressure of the boiler on the plate value, the more it compresses and it reduces the foam that forms on the top of that water. So what happens with carryover is when a boiler suddenly depressurizes or it's sudden high demand, effectively the pressure drop in the boiler allows the foam to increase on the top. This is from chemicals and whatever else that we use to treat our boilers. That comes closer to the point of use, so on the crown valve, and can carry over into your system. So when you talk about those kind of things with carryover, we're then talking about more erosion, corrosion, damage to your pipeworks, which we will cover in a bit. So reduce pressures at process. If you're running your boiler below pressure, then you have less percentage above what you need. So you're more likely to starve the process. So the pressure and temperature relationship. So unlike thermal oil or hot water systems, temperature is controlled by manipulating the pressure of steam. So for instance, 1 bar would be steam at temperature at 120 degrees. And the specific enthalpy, so the HF on that would be 2,706 kilojoules per kilogram. All this information together with the enthalpy, both steam and water, can be found in the steam tables. So anything below that line is water. Anything above that line is steam. And then you have the more temperature you add to it, you then start superheating. So pressure and temperature relationship. So again, as we see here, most boilers you will find will run between 7 and 10 bar. I know there will be a few of you that are running at 13 bar or maybe higher. But because of the compressibility of steam, as you see from 7, the curve starts to straighten. So you are adding more heat, more pressure, but seeing little gain in the specific volume per cubic meter of that steam. So in effectively, a 10-bar pipework is very similar to a 14-bar pipework, but it's cost you more to get there. So we'll cover pipe sizing. So there's two methods effectively of pipe sizing. So one is the pressure drop, which you can see on the screen here. So the idea with this is following the lines, and where they intersect, it gives you your pipe size. So as we can see here, you've got 10 bar, we've got the P2 value, and it gives you, in this particular case, a 0.2 pressure drop value. So you would follow the line across on the steam bar side. So we're talking on the left-hand side. I hope you can see my cursor. So at point A, take it over to here to where your flow rate is, draw a line straight up, and where it intersects the pressure that you've just found, there would be your pipe size. The other version is velocity method. What I should say actually before that is that the pipe sizing method on pressure drop is more for main steam lines, so longer runs when you're doing 100 meters or so. The velocity method is more for process, so shorter runs, because you don't see so much losses on a shorter run. So again, this one's very easy. You would find the pressure you need and the meters per the velocity, the meters per second that you'd like. We always recommend 25. Follow it across to the load that you wanted, go up, and it gives you your pipe size. So there is two versions of this chart, one for schedule 40 and one for schedule 80. So we wouldn't really recommend the use of 40 meters per second. When we inevitably add to the plant, that 40 meters per second can quite easily become 60 meters per second, and then you start talking about damage. So condensate, what is condensate in a pipe? So we think of it as a liquid, but it's not really. So this shows a cross section of a condensate pipe with flash steam in it. The condensate should not be thought of as 100% liquid. So in this example, it shows here that you've got about 99.6% of the total volume within that condensate pipe is actually flash steam. So this is based on the figures that you see there. Hence why many of you with your condensate recovery units will see the flash steam that comes off there. There's that energy there still. And that's just what a condensate pipe is. It still carries energy. So before I move to the next slide, I just want to take just a moment to ask if there's any questions. Anthony, has anything come up on the chat yet?
Nothing yet. I think we are good to proceed.
Okay, no problem. So flooded gravity condensate line sizing. So this is talking more about wherever you have, say, heat exchanger, prime example. They're quite open to stool flooding. Many of you would seen a leaking easy heat, heat exchanger in your site at some point. So how do we combat that? How do we pump that away and make sure that those stay dry? So on here, as you can see, we have a graph here. So undersizing would give you high resistance, choke flow, risk of waterlogging. Oversizing is, again, just as bad in some ways. It's a higher cost. You get a higher pressure drop. You get more flash steam. So how do we balance that? How do we make sure we get the right one? Well, as you can see in this example, so we have a condensate load of 4,600 kilograms an hour, and the lifting condensate from a mechanical pump. So here it's done on the maximum value for the pump. We take it across, and it gives you the on this very simple one, it gives you the pipe size that you'd require. That's based on your lift and based on your lift and your load. I would like to add that all of those are available in our TI sheets as well. So if you have a product and you're unsure, flick through the technical information which is available on our website, and you will find those graphs. It would be the same for any other manufacturers. Most manufacturers will publish those graphs on their technical information sheets and their installation manuals. So combining the gravity and a pumped line. So how do we do so? So as you can see, the example on the left-hand side is a gravity line. So you have the condensate drop into the pocket. From the pressure behind it, make its way through the trap, and then it end up in the condensate line. But there is a lift there. So there is the potential for stall. It will vary very much. It's a very generic term there. I'm just using that term just to highlight the pumping. On the right hand side, you would see our MFP pump. So it's a way of being able to mechanically pump that condensate so that you don't get stall, you don't get waterlogging. Here you can see that we've taken the trap set, so which would be somewhere over here, into a vessel, so a condensate receiver, which is then being fed into a pump, a mechanical pump, with a motive steam line, which I don't think is shown here, so we can pump for over, say, if you had a 10-meter lift going up to the top of a building or back to a feed tank. So we have the APT as well. Many of you have these on site, so I imagine you've seen them before. So this is one of our automatic pump traps. As you can see, the features and benefits of the operation are low cost competitors on the competitors in market. The first sizing of the pumping trap, there's only really one size, and that's it's 304 mil high, and it's a DM40 inlet with a DM25 outlet, so it's relatively easy to specify. We can do materials of SG iron with stainless steel internals, and the connections can be screwed or flanged. The motive pressure can be steam up to 13.8 bar, so that's 198 degrees C, and it's quite a small unit, doesn't take a lot of room. So mechanical condensate recovery pump, so this is, in this case, is using our MFP, so it's kind of a larger version of the APT. There's a little more to that, but we'll cover that in other webinars. Again, same sort of thing. You've got your condensate coming in, being caught in a receiver, go into your pump. When you're in a stall condition because there's a vacuum or there's some reason why the pressure has dropped over here, motive steam kicks in, pressurizes the line, and kicks the condensate out. So it keeps it constantly moving away from stall. The pros on this, so there's no electrical installation. They're ATEX safe. No electricity to unit means that there's no energy being used there. Uses plant steam, so you don't need to give a separate line, and can recover higher than 100 C of condensate without cavitation. So it's a relatively robust unit. However, there is cons. There is downsides to these units. Can only move a small quantity of condensate. It can only operate when motive steam is available, so the boiler is turned on. If your system's off, there won't be any pressure in the line. You're not moving any condensate. So we have the electric condensate recovery pump. I will say that these three products that we're showing you, although we're talking about the Spirax ones, they are available from other sources. Many of you would have made the one that you see on the page now, buy a couple of pumps and a receiver vessel. So as you can see here, we have electrical pumps. These are better for higher lifts, longer runs. We have this overfill with a U seal, so this is very important. I quite often see these too short. This is designed as an overflow, not a vent for your steam. So if you see steam coming out of this end, chances are either the water has been removed from this U seal, or the U seal isn't long enough. So if you see that, I would suggest check if there's water in there. If there's not, fill it up. If there is water in there, you wouldn't get steam. If it keeps on blowing the water out, this tube needs to be longer, just to give more pressure on it. And again, these are open to atmosphere. Sorry, go on.
Hi, Nick. We have a couple of questions so far, so
yeah,
maybe we can just shoot them. And okay, the first one maybe would like to hopefully use a pointer during a presentation. I don't know, we are not able to see the pointer, so maybe you can switch it on. But when looking at the questions is from Kevin, Kevin has a diesel boiler. What would be the best way to reduce his daily consumption?
On a diesel boiler,
Yes.
Efficiency effectively. So the boiler itself isn't the issue, it's the pressure it's run at compared to the load that it needs to supply. So there's various different ways. If you find that your process is starved, say there's a road torque or some kind of oven that you have on your system. Say that you're making rice for this case, but you find that you have to throw away a lot of product because it's spoiled because the temperature has dropped. If you have effectively non-critical lines on there, one way, it's not the only way, but one way is you could put surplus in valves on the non-critical so that you maintain the critical process, which is the rice, is always supplied. But again, it's going to be efficiencies. It's any efficiencies you can make in the system, anywhere you can save a leak or you can insulate a pipe, just to make sure that the heat that you require, the load that you're getting from your steam, when it reaches point of use, is as best quality and as high a temperature as possible. So adequate steam trapping, which we'll cover in a bit, separators for dry steam, the right kind of trap as well. So different traps are designed for different applications. Again, we'll cover it a little bit more later in these slides, but for instance, a thermodynamic trap, majority of the time would be main lines drainage. The reason being is you see a relatively small load on main lines drainage compared to, say, down and process. So the trap can be more condensed, it can be cheaper, it can be less complicated. But if you're in the oil and gas industry, let's say, and you are doing heat tracing on pipes, majority of the time you're going to be dumping that condensate, you're not going to be returning it to boiler. So when you dump it, you want as much temperature, so as much energy out of it as possible. So you would use, say, a bimetallic trap or a balanced pressure trap that has effectively holds more condensate behind it before it releases. So that condensate can get cooler and that energy can transfer to your, as we were saying, it was oil and gas, into the crude oil to change the viscosity. Hopefully that answers your question. It was there. You said there was another one as well, Anthony, didn't you?
Yes. Another question is, so if 99.6% is flash steam and not liquid, could that be the reason why the liquid, that is a condensate return in the hot oil, is lower? Hot oil tank is lower.
Again, it depends on your installation. So I quite often see the return pipes going into, say, a feed tank for preheat on the water not being long enough, and they don't tend to have recirc pumps. So what you find is the condensate comes back, it sits on the top of the tank, the top layer of the tank. So your hot water sees there, and you see a lot of flash steam come off the top of the feed tank. But where you're pulling down the water for your boiler tends to be near the bottom. So you're constantly pulling the cold water, not the hot condensate you've returned. A way around that, like I said, is a recirc pump. So a very small pump. It's just effectively pulling your condensate, pulling your water from the bottom to the top and mixing it. And then you see a reduction on the flash steam that you see come off the top of the tank. Another way is a deaerator. So we sell a kind of a unit that sits on top of there. It sprays the condensate in with the flash steam load and allows it to pick up the heat and then returns it to the feed tank. So hopefully that answers that question too.
Okay.
Was there any more? Yeah.
Yes, there's one more. Would you always use an MFP pump on a heat exchanger?
Not necessarily. I would suggest probably the APT is better because the load is smaller. There is ways round of not using a pump trap. So quite often heat exchangers are fitted very close to the ground. So they're sat on a skid or some kind of plinth, which only leaves them a few inches from the floor. Because you have no drop out of the heat exchanger, you have stall. So you need can have stall because you need to remove that condensate. But equally, if you had the ability to raise that heat exchanger, say 2 meters in the air, 1.5 meters, potentially you could create enough head, so the drop from on the outlet down to the pump trap, that you wouldn't require a pumping trap, a mechanical pumping trap, so just a normal trap. But again, it depends on your load. If you can, the better installation is always going to be if you can put the heat exchanger higher. Because even if then you get stool still and you still need an APT, you've got a header on the APT, so it would run more efficiently. But equally, an APT is designed that it doesn't need any header either. I'm just talking about best case scenario, best installation. Any more questions?
I think so far we've answered the questions. We can proceed, yeah.
No problem. I will stop again shortly for more. So please keep those questions coming in. We love your questions. So I think we've pretty much covered condensate on the CRU. Yep, go on.
Sorry, there's just one which has come in. For
Yes.
condensate recovery, there is a power plant setting with the flash steam tanks with condensate radiators for cooling. Other settings don't have. Does that have any effect on the efficiency of the condensate recovery? Let me just repeat the question, yeah? For the condensate recovery, there's a power plant setting with the flash steam tanks with condensate radiators for cooling. Other settings don't have. Does that have any effect on the efficiency of the condensate recovery?
So I'm trying to understand the question properly. So is the flash being used for heat exchangers, or are they cooling the condensate? Or preheating something. If you have a heat exchanger in any place, the chances are it's because you're trying to recover that energy, that heat that's in the load anyway. So it makes a difference, or potentially makes a difference, on your temperature in your feed tank. But if you're reusing that energy somewhere else, I would argue you're being efficient just at a different source. Again, I mean, the more we can preheat the water going into a boiler, the less chemicals we need. So deoxygen, oxygen scavenger chemicals, and the less thermal shock we give to our boiler. So the less chance of carryover and loss of pressure at point of use. But again, it would very much depend on your installation, because the pros for the way that you're doing it may be higher than the cons for not returning it to the feed tank. Hopefully that answers that question. Is there any more, Anthony?
No more. I think we can proceed.
Okay. So what we've covered so far is pipe sizing, so we'll move on to strainers. So strainers are important. We want clean condensate, clean steam. We things like materials that are left over in the pipe, so the general wear and tear of a pipe, whereas it erodes, does and can do damage to valve seats. It can block steam traps. So we want some way of removing that, making sure it doesn't pass down the line. Of course, if you're running products, you don't want those particulates to make their way to the product that maybe it's coming in contact with. So there's two ways to install a strainer. As you can see on the left-hand side, the top image, that would be what we would suggest for steam. The reason being is, in any steam pipe, regardless of how good it is, you will have a slight bit of condensate until it hits the next drain point. With the strainer this way round, it means that the condensate can't accumulate like it could here, which means it then passes down and it reduces the potential for water hammer. Condensate, it's a liquid, it's not the same issue. So I know we spoke about flash steam, but we still treat it as a liquid for condensate lines. So we would hang this down, because as the water passes, it drops the particulates into the strainer and moves on. This shows the incorrect on a steam side. So as I was saying, you've got your condensate in your pipe. This is filling and increasing the potential for water hammer down your line. So we will cover now line gradient. So next to traps, right, trapping in the right place, and the things I would say this is probably just as important. So main large drainage is actually covered. I don't know what the local legislation is, but in Europe it would be EN 45510 and section 4.12. So that states there should be a drop in your pipe over a distance, and it's a 1 in 100. So for every 100 meters, it should drop by 1 meter. That allows for condensate to any condensate that's forming is to run off, hit your pockets and hit your trap sets. It also is good for startup, and if you have this arrangement as you're preheating, as you're heating your system, condensate is running away as the pressure increases, so you have dry saturated steam. Trapping should be every 30 to 50 meters. That's based solely on the gradient, effectively, or it's not just solely on the gradient, sorry, but it's the kind of the recommended because they're tied to that. And this is how you would distribute a line. This is greatly exaggerated. You wouldn't see this kind of drop. A 1 in 100 would be barely noticeable. But for the sake of the animations, to make the point, we've exaggerated the drops here. So next, we'll cover trapping. So main large drainage, as we were saying before, this is why the different traps are suited for different areas. So as I was mentioning before, the TDs, they deal with the low loads. So the reason it's a low load is we expect 1 to 2% of steam generation to become condensate in a main line. So at that percentage, the trap is not going to deal with large loads. It tends to be higher pressure, so they need to be a little bit more robust. But they won't see the same kind of condensate you will in your process. Here, as you can see, so this is a process heat exchanger. Steam generation, we expect 98 to 99% of that steam generation at point of process to turn to condensate. You're only getting rid of the condensate because you've used all the energy in your process, and because it tends to be the end of that leg, end of that line leg. It's not going anywhere. The only place is to return, and how it returns is by condensate. So size and drain points. So every 30 to 50 meters, so it ties into trap sets or traps. Natural low points in your system. So if your factory is on a hill and there's a slight gradient, be aware of that. Be aware of the drop may need to be slightly higher, just to compensate for that extra climb. Low points would be like we were showing, where you're then going to rise a pipe. So if you take a sudden corner, sudden 90-degree angle and lift up the pipe, say a meter, or to go over a roof void or any kind of building structure, that would be a natural low point. So you would need drainage there. So horizontal takeoffs should be around from the bottom of the pocket, should be at 30 millimeters above the pocket. This is for the trap sets, and it can be up to 100 on mains. The reason being for that is a dirt pocket is designed to capture dirt, so you don't want to drag that through your traps. So by lifting them slightly up, you're allowing the condensate to fill in the dirt pocket, but drop the particulates, the dirt that's in there. And then the traps can take away relatively clean condensate. So the size of the leg, so the size of the pocket should be equal on mains, so up to the same size on the 4-inch line. On others, I think it's up to 75. It should be 75% of the size. The reason pockets terminate vertically, so straight down for the pocket. Trap sets will come straight off horizontally. So for size for condensate load under startup conditions, so this is very important. When you're starting up, when you're warming up, almost all your steam is being turned straight into condensate. So as a general rule, if you have a 100 kilogram load on your trap under normal conditions, for startup, double it. It should be 200. It should be sized on 200 kilograms an hour. That allows you for the runoff, the removal of the condensate as quick as possible when you're warming up, when you're starting up. And again, this demonstrates, as we were showing, so pockets should be wide enough that the condensate drops in instead of flowing over the top. And then with the pocket slightly raised, the dirt is deposited here, which eventually gets blown down or cleaned, and cleaner condensate then flows through your traps. So challenges, so footprint, installation length, assembly of and installation time. So traps, because they are multiple pieces of equipment. You've got isolation valves, you've got strainers, non-return valves, the trap itself. Yeah, they take time to assemble. Normally to service them, you have to undo many different threaded connections and pull them apart to get to the individual part. So there's the potential to put them in the wrong order. We've all done it. We've all been working at home, I know, taking the screws out of a TV or something like that and forgot maybe 1 or 2 screws. I know I certainly have. There's always more parts left over when I've taken something apart and put it back together than when I initially had the item in the first place. And offline servicing, you have to isolate it, turn it off to be able to service it properly. Dissimilar metals, so different metals when they meet will corrode differently. Some will interact with each other, which actually speeds up the corrosion. So by using, say, SG iron, carbon steel, you can potentially introduce more service needed because of the way those metals interact with each other, and they're not suitable for hygienic environments. Weight and aesthetics, design specification, they're all things that make these trap sets more difficult, not necessarily difficult, but more difficult than to specify and correctly position. So Spirax has recognised this. Other manufacturers have too, and we actually offer what we call is the steam trap manifold. So in this particular case, it's called an STS 17.2. The idea with this is actually was born from safety. So many trap sets will tend to be above you, maybe 2 meters high, or on main lines especially. If you've got to go up a ladder and service these, you have to be up that ladder until you've completed the work. The argument is the danger that poses. So health and safety, the first point of trying to make something safer is to try and eliminate the action. So if you can't eliminate, you try and minimize. So with a trap station rather than individual equipment, your time up that ladder, for instance, would be shorter because there is only 2 bolts to undo for the trap to change it. Therefore, effectively making it safer because the time that you are in danger is minimized. These are online servicing, so you can take these off when running, isolation obviously, but take them off, replace them. They're stainless steel, so they last forever. They're hygienic because of the materials that are used, and they're heavy actually. I mean, this says they're lightweight. They are heavy because of the materials they use, but in comparison to the same equipment individually, they're probably slightly lighter. Aesthetically pleasing, I don't think that really matters when it comes to a trap set. I mean, as long as it's doing the job, I don't really care what it looks like. But the design and specification is relatively easy too. So we will now cover separators. So when it comes to separators, there's different ways you can specify them. They're very easy to specify a separator at the right size. So if you're using it on a boiler, you would size for 75% of the steam dryness. So if you had 10,000 kilograms an hour from your boiler, 2,500 would be condensate. So you would size the separator to suit. If it's on process loads and off main lines, near say a CV or a PRV, so control valve or pressure reducing valve, using assuming that the velocity is okay, using line size is perfectly adequate. It's perfectly fine. So how a separator works effectively, as you can see here, there's a series of plates that's in there. You have your steam coming in, which is carrying droplets of wet, droplets of water. It could be carryover. It hits the plate. Sorry, I don't know if you can hear me. Those droplets then hit the plate and drop out the bottom of the separator because there's a trap set there, allowing the drier steam to move around the plate and then move to the further down the line on the outlet. Most importantly, though, all these pieces of equipment should be insulated. The reason being, you want the heat transfer that's going through them to be as high as possible. So air vents. Before I move on to that, I'm going to stop again and see if there's any questions. Anthony, is there anything on the chat?
Yes, we have one question, and the question is, when designing steam pipelines using the pressure drop method, how do you determine P2?
Most TI sheets, technical information sheets, will give you the pressure drop through a piece of equipment. So as a standard figure, you can use, if you do not know, you can use a pressure drop of 0.2 across each item. But the TIs, the technical information will give you the actual figure. And then it's a case of adding those up and giving you your P2. Any other questions?
No more questions so far.
Okay. So we'll move to air vents. Again, guys, keep those questions coming in. We're here to help you as best as we can. The reason why we do this training is to help you with your processes. So if you think of anything, please don't hesitate. Put it in the chat, and we will address it. So air vents. So air is dangerous to steam systems. The reason being is as soon as you have air in there, you cause corrosion by forming carbonic acid. Insulates heat transfer, so it makes your system less efficient. So although at times we will need to introduce that there into the system, especially say you have a steam system, you're cooling down, you're turning off. As that steam collapses, it will pull a vacuum and it will try and find that air from any source it can. And most of the time it ends up being on gaskets. So if you walk down your steam line and you see many of your gaskets leaking, it's probably because you don't have a vacuum breaker relatively nearby. So no air can get back into the system. So it's just trying to pull it from the closest place, the weakest point it can. Again, like we were saying, air is also the enemy. So when that system is heating up, we want a way to remove it. And that would be via your air vents. So this graph kind of indicates very well the various different preventions we have to passing on that heat, that enthalpy onto your process. As you can see here, we've got steam at 1 bar G, so 121 degrees. The drop here from the energy loss is significantly higher than with any other layer. So that air film, that insulation is insulating there and preventing you from warming product. So as you can see here, you've got 99 degrees on product. You've lost 22 degrees just there. Again, there is other things there. You've got condensate film, may have scale, you've got the metal or the material of the actual vessel that you're heating, scale on the other side of there, and product film here. So this would be on a effectively a cooking vessel. They do all have drops, but none of them are as high as that air film. So again, it's just demonstrating it here. 100% steam here is 120 degrees. It's 121 degrees. As soon as you introduce, say, just 25% air, 75% steam, you've lost a significant bit of temperature. You've gone down to 116. So if your system or your process is temperature critical, your pressure gauge will still say 1 bar G, but your temperature has dropped. And that's more than likely, not always, but more than likely because you have air in your steam system. So again, air venting, we want to remove that air. We want back to 100% steam so we can have that high enthalpy, that higher temperature. So where to locate those? Here, as it says here, end of distribution lanes. So right over here. Natural high points, anywhere that's would accumulate air and it can't can't move further down the system. And that process. So here, as we were talking about with the steam cooking vessel, a high point would probably be here. So we'd put an air vent on that side there. That would allow all the air to evacuate through the vessel and remove here, and we've just got steam. So we've now covered all 1 through to 1 to 6, and we're going to talk about minimizing water hammer. So in steam, as we said, there is always a slight bit of condensate forming either on the main lines between traps or more locally heat exchangers or various other items. So the challenge we have with that condensate, the more we have there, as the steam moves over the top of the surface, there is a friction that is an energy that's given here between the steam and the water, which picks up a speed. So over time, that friction, that pull on the surface of the water will form almost a wave. And then when it reaches a point that it blocks the pipe, you have all this pressure from steam behind this slug, and it shoots down here. So if you imagine Tom Cruise in his fighter plane going down this pipe in Top Gun, that could be at Mach 1. It could be traveling the same speed as he is. And of course, when that hits a closed valve, a piece of equipment that for any reason changes direction, it's going to slam into that surface, and that's why you hear the bangs on sites. Pipes rattling would be another sign. It's dangerous for many reasons. If it cracks equipment, you would have the venting of steam there, or it could be fail to isolate properly. So when you're working on the line, many different ways it could cause serious harm to not just you but your process. So again, when we do talk about reducers as well, there is a concentric reducer that you could use on a condensate line, but you wouldn't use it on a steam line because this step here would allow for more buildup of condensate here, so more opportunity for water hammer. By using an ecocentric reducer, we have the flat surface on there, so there's no buildup, there's no extra step, and that would allow us to correctly remove that condensate afterwards via trap sets. So branch lines, again, this is another case where we can pick up condensate, we can make our process use wetter. So on occasions, we see the tapping off of the branch coming off at the bottom. So that means that it allows condensate to flow down the line. By tapping off of the top, it means that the condensate is at the bottom of the pipe and we should only be getting steam through here. So it's protecting your process, keeping that enthalpy as high as possible. We would normally also try and make sure that the pipes are sized for 25 meters per second, if say 10 meters long. Just because I haven't asked as much and there's not so, no, we're making good headway through the slides. Do we have any other questions at this point?
Yes, we do. And I'll start with, do you always install air vents and vacuum breakers at the highest points on a steam line?
So yes. So the reason being is, if you imagine a helium balloon, we've all had them as kids or seen our kids have them. They float above the surface. So effectively air does the same thing in a steam system. It's not quite as simple as that, but it's the easiest way to explain it. As it passes through your steam system and it hits a high point, the air becomes trapped in that area. Steam passes through, but the air never moves on. So when you use a high point to evacuate air or to break a vacuum, the vacuum breaker is more forgiving. It could be anywhere else really, but if you're doing a tap in for an air vent, you might as well put a vacuum breaker there too. That allows you to drain it and get rid of that insulation factor. Hopefully that answers that question. Any other questions?
Yes. Should air venting be continuous or just upon startup?
So it would just be on startup. Well, yeah, your air conditions are going to be on startup because your system's cold. You've introduced air in there. So the air venting, you'd see most of it on startup conditions. I guess there's certain processes where you could potentially see more air. I would say maybe on APT traps, it's not unheard of to, instead of use motive steam, you can use compressed air. So that may introduce that. But again, at some point that pipe's open to atmosphere and it's a condensate pipe, so it shouldn't be an issue. I would suggest 9 times out of 10, with some exceptions, it will only be on startup. Hopefully that answers. Next question.
Where are the best position to install the vacuum breakers? Does the air vent serve what the vacuum breakers will do, or will you need both installed in the system? Those are both two questions.
So ideally, you need both. Because of the air steam density ratios and things like that, the air vent will only work or will stop working when it sees steam, whereas the vacuum breaker doesn't rely on the fact that there's no steam there, just that there's a vacuum pulling on it. So you would need both. Because you're already doing a tapping for an air vent, that's probably the best place to put the vacuum breaker as well, only because it saves installation. But that doesn't mean you need hundreds of these things. You only need them at certain points. For instance, on a main steam line on a relatively length from, say, medium-sized factory, I would suggest you probably only need one or two of them, and then most of them will be near the end of line or any point where you have a rise and then a drop. So yeah, like I said, these wouldn't be as common as traps around a site, but they should be there. Again, on process, you would need one. So on a heat exchanger, for instance, you would put a vacuum breaker. The reason being, as the control valve closes, because the heat exchanger has reached temperature, it would pull or would create a vacuum or a drop in pressure on the inlet. So you would want to effectively rebalance that pressure. You'd put a vacuum breaker there. That would prevent a little bit the stall backing back up through the heat exchanger. And then if you've added air into there, an air vent as well to remove it. So process is probably where you would see most of them. Hopefully that answers that question. Any more?
I think you may have answered the last one by the last statement, but anyway, I'll still ask it. What effect will you have in the system if you have an air vent installed and no vacuum breaker installed?
Yeah, so again, it's the same sort of thing. So you would get rid of the air, but you don't prevent the vacuum pulling on shutdowns or after control valves and things. So you, depending on where it is, you would either have the breaching of gaskets, or you would have stalling heat exchangers or various other equipment. So you do need both because they're two different functions. Any more questions?
Thank you. So no more.
Okay, yeah. So we're in the final quarter. We're on the last leg, and we've approached the top of the hill and now walking back down. So 8. So we're on safe isolation now. So many of you would have seen these kind of valves on site. So these are the bellow seal valves. Give very tight locking, especially if you've got the balanced pressure versions for the higher pressure lines or bigger valves. Easy to use, relatively easy to maintain. Of course, we also have ball valves, and when I say we, I mean the industry. There's ball valves, gate valves, butterfly valves, many different forms of isolation. So it will be what's best for your process. We at Spirax, we have the BSA valve, so hence why it's shown on the screen. To us, in our experience and our industry, we found that these are the best form of isolation for a steam line, next to a ball valve. Ball valves are almost unbeatable, but they can be expensive, especially the larger you get. So there is a big move these days towards double isolation. The argument is to prove the isolation you have online. So if you have a leaky valve here and you have one valve that decide to work on the line here, you could assume that because this is isolated, you don't have any steam here. But if this is passing, as soon as you open this, you're going to get burned. So how do we prove the isolation that we have there is working correctly? So you would do this kind of arrangement. This could be ball valves, it could be gate valves, but it's just the free valve movement. So you'd have two, which are the size of the line. Well, this one could be significantly smaller, say 1/2 inch, 1/4 inch. You isolate both valves, so therefore the pressure drops downstream. Upstream, we hope the pressure stayed here. By opening this valve, if there is no steam that comes out, you've proven the isolation. So that means it's safe to work on. But if you are updating an old line where you have the single point of isolation there, but you want more modern ways, you want to be able to prove this, you want to make it safer and only have this space. Now, the face-to-face dimensions on BSAs are very similar to many other pieces of equipment and many other manufacturers. There's a standard there. So just because you don't have a BSA but you have another form of isolation valve does not mean that the face-to-face value has changed. It may have, but more than likely probably hasn't. So we do something which we call the DBB3. So it's the double, block and bleed, and the 3 stands for the material grade. The idea behind this is that you have a face-to-face dimension, which is the same as the equipment you're looking to replace, but you still have the double isolation and the bleed. So you can, there's no need to change pipe work along with this. So it's 3 components combined. So it makes it much easier to install and replace, but it also gives you your proven isolation, your double isolation. So we'll move on to warming the system up from cold. So we touched upon this earlier. How are we doing for time, Andy, as well?
We are midday. It's midday now.
So we've got about 5 minutes left. Yeah. So I'll rattle through this a bit quicker. So warming the system up is probably one of the most important things you will do. It's also probably where the most danger is, because you're taking a cold surface and you're making it hot very quickly. So it must be done by a competent person, so they have to know what they are doing. It should be done with a full risk assessment, and it must be followed to the letter. Method statement, operation must be produced. Generic ones will not work because your processes are different. Just like every person is individual, every process is individual. This needs to be assessed and assigned for your process, and it should be followed to the letter. Yeah, so the exact instructions you write should be the ones that you perform. So as we got with the crown valve, so you would slowly raise this to warm up the system. Now, I guess there will be, you can automate this. We offer automation on this, but you will have a set period that you open this valve, and maybe, I don't know, a couple of turns every 15 minutes or so on, whatever is really into your method statement. But then poses an issue because you've had a cold system. You have condensate, you have water drifting around. So you then have to open all the valves on low points, make sure your air vents are working properly so you can remove that condensate as quickly as possible, because while you've got no pressure, you've got no means to move that condensate through the traps. So we tend to open all our bleed points. It can be time consuming. If you have a large site, it takes a while to do all that and then to shut them all back off. So we offer a steam trap, which is called a number 8. So this works on temperature. So as soon as it starts seeing a higher temperature, it will close. You would put this, say, horizontally on a pocket, a dirt pocket, or whatever else. It would close off as soon as it starts seeing heat. So, but open when your system is cool enough, so it gets rid of all your condensate. These aren't to replace steam traps. These are to work in parallel with them. This is mostly designed for drainage, to make sure that engineer who was wasting 3 hours in the morning warming up the system by opening all the valves and then slowly walking around and closing them no longer wastes that 3 hours. He can use it better, running process, doing the service work he needs to, or it's just about taking the time we have and making the most of it. So this is one of the ways. So expansion and support, I'm going to rattle through this a little bit quicker just because I've noticed the time. So effectively here, if you find the approximate expansion of 15 degrees C between 15 and 100 on 100 meters of carbon steel pipework, distributed at a temperature of 265 degrees. So the temperature difference there would be 265 minus 15 gives you 250 degrees. So we're the diagonal temperature difference of 250 cuts the horizontal pipe length at 100 meters, and it gives you your size down where your temperature is. So it gives you your size of the pipe that you require. Very simple for the size of expansion you require, the size of expansion you will get. Very simple, easy to try and negotiate. There's various different types. So here you have the flexi hoses. You have a bend where it will expand here. Again, similar sort of process, but with a loop. Again here, and these are the more complicated, more expensive options, I guess. So again, with support, how do we work out how much support? These TIs are available on pipe manufacturers. I think we have them as well on our site. Very easy to negotiate. So as you can see here, DM50 pipe with mild steel. Yeah, so you would look at the material requires support every 2.4 meters. So last part, safety. I would normally stop for questions, but because we're near the end, I'll wait. So safety valves. So we want to maintain a dry seat as possible in a safety valve. The reason being is that when this is used for a safety event, we want to make sure that it's in best condition possible. So we've got that full to make sure there's no accumulation of water. If you have this pipe going outside and it's facing upwards slightly, there is a potential for rainwater or anything coming in. Also, class 4 shutoff is a control valve, a safety valve. So you will see a slight whispering. These things will leak under normal conditions, just not much. But over time, that could build up liquid. Because you've got the full, as we spoke before, you need a drain point. And there is, on most of them, from most manufacturers, there's a bolt on the back to be able to drain there too. So we talk about blowdown. So when it comes to sizing blowdown vessels, you've got to make sure your load is correct. So as it says here, it's PD, so it's a pressurized vessel. Design pressure is at least 25% of the max is permissible for working pressures. Design temperature of tank should be the temperature saturated steam at the pressure equal to design pressure. So the pressure we talked about there. How they work, very easy. Your TDS or your bottom blowdown comes into the tank on this pipe. It mixes with condensate you already have there that's been sat in the tank, not being able to evacuate. As the level rises, cold water exits the pipe and drops out. So that the idea is that we try and keep it at that 43-degree max temperature to drain. There's temperature probes that are on here as well, which will give you a cold water feed as well to drop that temperature if it's too high. One thing I will say before moving on there, if you have 2 boilers, they should be sequenced in such a way that they can't blow down at the same time. One, that saves you cost. Your vessel doesn't need to be so big, but also it's to do with safety as well. So this should be only blowing down 1 boiler load at a time. This is the arrangement of a blowdown vessel. So as you can see, there's the air vent there to keep it as an atmospheric pressure vessel, although it's still under PD. Inspection hatch, these things will erode just like a boiler does, so it still needs inspection on it. Pressure gauges, overflow, the cooling that we were talking about before with the temperature one, and a drain for when you need to maintain it. So we've now covered all of those. This is my final slide. If you guys have any questions that come up, we love this kind of stuff. Please feel free to contact us directly, and these are the contact details for us. So yeah, we thrive on trying to solve your solution. As engineers, if we see a problem, any engineer, if we see a problem, we want to fix it. So we're more than keen to help you fix your situation, your challenge too. So please make note of these contact details, and I will go back to Anthony for any questions.
Okay, so we do have one question. I will just give me a moment to read it. Basically, why is it that sometimes the valves leak when there's steam coming from the non-pressure side, or will they always leak as it's the non-pressure side?
So it depends what kind of valve you're talking about. So if you say a control valve with class 4 shutoff, so the class 4 shutoff is a metal to metal seat most of the time. Because of the 2 surfaces you have together don't completely seal, you will potentially see a slight whispering. And when I say whispering, think of it in terms of boiling the kettle at home. So you've just put the cold water in, you can just start to hear it make heat, and you see a slight vapor coming out the top of the kettle. So that would be the whispering you would expect to see. If you see anything higher, so if we're talking, say that kettle is close to boiling point and that steam looks like it's under almost a bit of velocity, a bit of pressure, then there's an issue. With the control valves, because I've just used that, the whispering is normal. Anything more than that is a failure. On isolation valves, they're isolation valves. They should be class 6 shut off. There shouldn't be any leakage whatsoever on there. So if you see any whispering on there, that's signs of wear, and it's signs of service needs to be done. So I think we touched upon it in our last webinar. Servicing valves rather than replacing whole things, so preventative maintenance especially, will be 30%, around 30% the cost of buying that item new. So if you can service it, you can get to it before it gets too damaged, it's going to save you money in the long run. So hopefully that answers that question.
Yes, I believe it does. Looks like there is no other question. So, so I think this is, we've reached at the end of our live event. And if you have any other question, please feel free to contact us. The contacts are on the shown on the screen right now, and also you can also contact your account manager, the sales engineers that we normally do have. Also, I would like to note that this session is recorded, so you will receive an email containing the link of this recording this afternoon, so you'll be able to go back to it, or you can, if something you did not understand, you can be able to go through it again. And within the email, you'll be asked to do a short survey. So we'll appreciate your feedback in the on the value that you have received from these sessions. So we really appreciate if you could do that. And if there's no other question, I think we will end this live event. Yeah.
I would just like to thank both Anthony and Cornelius for supporting this, and all of you for joining as well. So it is my absolute pleasure to present to you guys. So I very much enjoy it. So thank you for taking the time out of your day to join and pull up with my voice for an hour. So it's much appreciated. Thank you.
Okay. Thank you, everyone. And